Okay. So it's finally Friday. We're going to continue with the notes. We're going to go ahead and at least be able to finish up with the word problems we started yesterday, and then we'll get back to the packet on Monday. Just a couple things. Remember, Wednesday by 8:05 in the morning is the last day to retake the test from earlier in the week, if you would like to do so. Coming up next week, we're going to go ahead and start the unit circle, and very quickly, we're going to go ahead and begin what I call mad minutes. Okay, we're going to start off this first week with just the trig ratios. So I'm going to give you a very short amount of time to go ahead and write down all 6 of the trig ratios. And then as we push into the unit circle and we really start to get acquainted with the special right triangles, I'm going to go ahead and have you evaluating these trig functions, either using the unit circle or the triangles. And it's going to take us probably about a month and a half doing it every day, and it's going to get old, it's going to get monotonous, but I guarantee by the time we finish, you're going to be very, very good at it. You're going to be really comfortable. Okay, so that's going to be starting next week. The other thing, we're still, a couple weeks out, but I'll go ahead and mention it. It's already mentioned on the website. The second exam for the 6 weeks, because I'm going to go ahead and submit progress reports today. We're already halfway through the second 6 weeks, so basically halfway through the semester. Your exam is going to be on the 25th, so 2 weeks from yesterday. That's going to be your next exam. In fact, it's the week where you don't have to come in that Monday, because us teachers have a content focus session on that day. Okay, and I think that's all I got. Unless anybody, did I mention the quiz next Thursday? Okay, so the quiz next Thursday is going to be over this material right here. Arc length, area of a sector, and circular motion. Okay, so there we go. I think that's everything. Okay, now I believe your class was the only one to actually get through 2B, correct? Okay, so we got 13.4 miles per hour. Okay, good. All right, well, very quickly, let me go ahead and review with you guys. Okay. So let's see, yesterday we were talking about 2 different topics. We had, arc length and then our circular motion that I just previously mentioned. So what was the formula for arc length? Okay, Satish. R theta, okay, and what variable do we use for the arc length? S. Okay, so S is my arc length, and it's R times theta. The only requirement is that theta, the angle, be in radians. Okay, there we go. It's not allowing me to write on the board today. So it's got to be in radians. So we went through those first 3 examples, and everybody seemed to be doing pretty well on those. Now, when we get to the circular motion, there were 2 parts, the angular velocity and the linear velocity. Now, the linear velocity is the actual speed of an object, but it's how fast it's traveling in a circular pattern, how fast it's going in a circle. Now, angular velocity is going to be how fast the angle is increasing with respect to time. Okay, so there is a difference between the 2. Now, for all of these problems, we always wanted to go ahead and start with the same ratio. We needed to know the number of revolutions and how long it's taking. Okay, we need to know the number of revolutions with respect to time. Now, what we're doing now is creating our angular velocity, but we like our angular velocity to be what? How do we like to measure it? It starts with an R. What's equivalent to degrees? Radians. We like them to be in radians. So this second fraction here, you're going to see this a lot throughout circular problems. So 2 pi radians in 1 revolution. See, your revolutions are going to cancel. You have radians per time. Could be second, could be minutes, could be hours, could be anything. But if we were to stop right there, that is angular velocity. Okay, Dylan, what's the variable we like to use for that? Okay, Raphael, can you help him out? It's a Greek letter. Omega, okay. We like to use omega. It looks like that curvy W right there. Now, if I have the angular velocity and I want the linear velocity, I only have to do one thing. Okay, multiply by the radius. As soon as I multiply the angular velocity by the radius, Now I have linear. Now remember, at this point, the radius is going to have some unit of length, some measurement, inches, feet, millimeters, whatever. So at that point, the radians disappear, and then you've got your length per time. What's the variable for linear? It's what, Satish? No. V, there we go. We like to use a V to represent the linear velocity. Okay, so this is what we were talking about yesterday. So let's take a look at number 3 right here, since we were done with 2. We're talking about a DVD. Find the angular speed of the DVD in radians per second if the disc rotates at a rate of 3.5 revolutions per second. Okay. So remember, these problems, even if you're not asked to find the angular speed, you want to go ahead and find it anyway, because you can't find the linear without the angular. Okay. So what's the first fraction I should set up? Yeah, we always want to start with the revolutions per time. So here we have 3.5 revolutions per second. Okay, now again, we like our angular velocity to be in radians. So what's that same fraction we're going to see over and over again? 2 pi radians over 1 revolution. That's exactly right. See, now my revolutions are going to cancel, and I've got radians per second. Okay. So all I got to do is just multiply this out. So 3.5 times 2 pi will give me 7 pi. But let's see what that comes out to. 7 pi. 21.99, so I'd be safe probably saying 22 radians per, what do we say, second. Okay, there we go. So there's my angular speed. Now, just like on number 2, the previous one with the bicycle, for part B, I can't use the angular speed that we just found because we have a different number of revolutions per second. If the DVD player overheats and the disc begins to rotate at a slower rate of 3 revolutions per second, find the disc's linear speed in meters per second. All right, so Miriam, how am I going to start this problem? What's my first ratio? Okay, now we are going to do that, but we'll do that in just a second. Okay. We could go ahead and start with that one. Okay. So 2 pi radians in 1 revolution. Okay, so this is going to guarantee that we have radians. Okay, but how fast are we spinning? Okay, 3 revolutions per minute. Okay, or second, excuse me. 3 revolutions per 1 second. Okay, so these revolutions are going to go ahead and cancel. So this is my angular, but now this question is asking me about the linear. What was it we said just a second ago? You multiply the angular by what? The radius, and what's that? Okay, 60, because we're told that the diameter of the DVD is going to be 120. Okay, so, just like I mentioned before, since you're going to have typically a lot of fractions here with your dimensional analysis, I like to go ahead and put the radius over 1 just to kind of make it flow nicer, whatever you prefer. So now if I were to go ahead and stop here, I'm going to have millimeters per second. Remember, as soon as you multiply by the radius, you have a unit of length. Here we have millimeters, so the radians are no longer necessary. We can associate radians with any type of length that we have. What do we want again? We want meters per minute. So let's take care of the easy one first. So let's go ahead and change the seconds. So what's my next ratio got to be? Okay, 60 seconds over 1 minute, because we want the we want the seconds to cancel. So now we're in millimeters per minute. Now, how many millimeters are in a meter? 1,000. Okay, very good. So if I want the millimeters to cancel, I've got to put 1 meter over 1,000 millimeters. Okay, so now those are going to cancel. So it looks like I am left with meters per minute. Okay. Is everybody okay with how we set it up? Anybody not seeing where we got any values from? Okay. Well, let's see here. I need to take 2 pi times 3, so let's say 6 pi. Okay, so 6 pi times 60, so I'll say times 3,600. Okay, so 67,858, but I'm forgetting something. We got to divide by what? The 1,000. There we go. That's just going to move the decimal over 3 places. So I'd say we have about 67.9 meters per minute. There we go. And remember, this is circular motion, angular and linear velocity. Any questions? Anybody confused? Bless you. Okay, so let's do this. Okay, we got a problem here about a clock. It says a wall clock has a face diameter of 8.5 inches. The length of the hour hand is 2.4 inches. The length of the minute hand is 3.2 inches, and the length of the second hand is 3.4 inches. A, determine the angular speed in radians per hour and the linear speed in inches per hour. Okay, so what I'm going to go ahead and do is I'm going to divide you guys up into 3 groups. Each group is going to have a specific item that you're going to find both the angular and the linear speed for. Okay, I'm going to give you 6 minutes. At the end of that time, one person from each group is going to come up and show us what you found. Okay, for the angular speed, I want you to go ahead and leave that in terms of pi. Okay, so you don't have to approximate that for me. But the linear speed, I want you to go ahead and give that to me the nearest tenth. Okay, so just 1 decimal place on the linear speed. Okay, no decimal on the angular speed. Now, I'm going to go ahead and mention this. I'm going to make this a challenge problem. I'm going to have the results up on Monday, and I'll go ahead and show every class. But it says, if the linear speed of the second hand is 20 inches per minute, is the clock running fast or slow? How much time would it gain or lose per day? So here's how we're going to go ahead and do this. Now, this is for all the classes, not just this class. The first 5 people to come in on Monday morning during tutorials, not 5 per class, 5 total out of all the pre-cal classes. First 5 people to come in, show me their answer, but also show me the justification where they got it from, will be completely exempt from the quiz on Thursday. Meaning you'll just immediately get the maximum number of points. 105, you're done, you don't have to worry about it. But it's only 5 people. Okay, we're going to give everybody the same amount of time. I still got to talk to 8th period about this. So 7:45 is when the door opens on Monday. Okay. And then if there happen to be more than 5 people outside the door, we'll figure a way to kind of whittle it down. Okay. All right. So that is, if you want to go ahead and take a look at it. Like I said, I will have that up on Monday. So let's do this. Let's say, how about everyone from Ethan's row over? You guys have the hour hand. Okay, so for the hour hand, I need the angular speed and the linear speed. Then starting with Alyssa's row through Alex's row. All you folks right here, you've got the minute hand. Okay, every other row left, you guys have the second hand. All right, so I'm going to give you 6 minutes. Now, I'm going to go ahead and provide a little more incentive for somebody to come up. It's not as good as getting rid of the entire quiz, but whoever comes up for their particular group will automatically get the bonus on the quiz Thursday. Okay, and I'm going to make the bonus worth a little more this time around. Okay. So if there are more than 1 people in a group who wants to come up, you know, maybe rock, paper, scissors, or some way to go ahead and decide that. But I'm going to give you 6 minutes. So you want to make sure that everybody in your group knows how to solve the problem, because if nobody volunteers, I do have my random number generator. Okay? So 6 minutes, starting now. Okay, so everybody from Ethan to the front of the classroom, you have the hour hand. Okay, from Alyssa around to Alex's row, you've got the minute, and then everybody else has the second hand. Yes? Do what? A Venom-themed question? Okay. I'm going to go from the comic book, because at that point I probably won't have seen the movie. I want to go see the movie, but I have in-laws coming in this weekend, so yeah. The wife would probably get a little upset if I said, "Hey, I'm going to run to the store and not come back for like 2 hours." So, yeah. There you go. There you go. That's exactly right. Just couldn't find what I needed. Hey, that's actually a really good idea. Okay, so make sure work together, help each other out. Okay. Make sure that everybody could answer this question. Okay, so we always start with the number of revolutions in time. Each one of these items is going to be different. Yeah. 3 minutes left. Okay, make sure you're conversing with your group. Remember, the angular velocity we're going to leave in terms of pi. The linear velocity we will round to the nearest tenth. Radians per hour and inches per hour. One minute. It's already been 5. Yes. Time flies when you're having fun. 6 minutes. Okay, time is up. Now, it does not matter who goes first, hour, minute, or second. Do we have a volunteer? Do I need to go to the random number generator? Any volunteers? Flaws, are you raising your hand or are you? Okay. Susie, you're shaking your head yes. Oh, okay. Sure. All right. Okay, so I'm going to go into the random number generator. 10. All right, so Raphael is going to talk about the second hand.
Just like.
Do you want the headphone? Oh, okay.
Okay, so let's get the angular speed first.
Okay.
Just like. So we'll start off with.
Oh. Okay, he is absolutely right. Now, Raphael says that the angular speed for the second hand is going to be 120 pi radians per hour. That is absolutely correct. Okay. And Skylar is going to take over. He's going to do the linear velocity. So we have our angular 120 pi radians times hours. Per hour, okay, there we go. Okay. So that will already be in inches per hour. So he says 1,281.8 inches per hour. Absolutely right. He multiplied the length of the second hand by the angular speed. That is absolutely right. Okay, good. If both of you gentlemen will sign this piece of paper, so I know who to give the bonus to. Okay, that's one down. We still need the hour and the minute. So Fawaz, you are volunteering. Okay, he wants to do the minute. Fawaz is going to do the minute. Okay. And Fawaz, would you like the headphones? No, you don't want to. Okay, he does not want to speak to the class. All right. Okay. All right, so I need the angular speed of the minute hand. Okay. So 2 pi radians in 1 hour. They're just kind of going past the idea of the revolutions, which is perfectly fine. Okay. So this is the minute hand?
Oh, yes.
Okay. 2 pi. Okay, so I'll go ahead and take that. We wanted to leave it in terms of pi, but that's okay. 6.28 is 2 pi, so he is correct. 2 pi radians per hour. All right. And Satish is going to help us out with the linear velocity, which we already have the 6.3 radians or 2 pi radians, whichever one you use.
And the question asks, to get it per inches per hour, so
Mm-hmm.
we can just multiply that by our 3.2 inches. And then you get rid of this, so that'd be
Okay.
basically you multiply that, that'd be 6. And then to convert that, that become equals 1 inches per hour.
Exactly right. That's it. You multiply the angular by the radius, and you've got the linear. 20.1 inches per hour. Where's that sign-in sheet? Who has that? Skylar, do you have it? Okay, well, I was going to make sure Satish signs that. Okay, all we got left is the hour. Hour hand. Who's up? Okay. Connor, you'll go? Yeah. Okay. All right. Now remember, if you have any questions or if you're not sure where something's coming from, please ask. Okay, at this point, Connor will be very happy to help you out. Okay, so for the hour hand, it takes 12 hours for it to go full circle. Good. Okay. That's exactly right. Pi over 6 radians per hour. Okay. So only 30 degrees an hour. Yes. Okay. All right, we still need the linear. You want to do the generator on that one? Okay, so let's see if we get hopefully one within this group. 27 will not work. 21. Is 15 within your group? Is it? Isn't that Ethan? Hey, that's what you got your teammates here to help you out, Ethan. But look at the bright side. You're guaranteed to get that bonus. All right. I'd like to thank Ethan for volunteering today. All right. Now, we've already got the angular speed. Remember, how do I get linear? Do we know the radius of the hour hand? Or the length of it, I should say? Oh, now that's the radius of the clock. What's the length of the hour hand? Okay. 2.4 inches. Now, remember, we're wanting it in what per what? The linear is in inches per hour, right? Well, the length of the hour hand is already in inches. Okay. So all we got to do is just come on up and get a product. Divided by? Okay, so we've got the pi over 6 radians per hour. That's our angular velocity. Okay, multiply it by 2.4 inches, which is the length of the hour hand. Okay. And 1.3 what? What's the 2.4 represent? Inches per hour. There we go. So he says the linear speed is 1.3 inches per hour. He is correct. Good. Where's that list? Who's got that list? Thank you, sir. Okay, so Ethan signed that, and Connor, make sure to sign that as well. All right, good, good, good. Did anybody have any questions on any of those three? Okay, is anybody already thinking they're going to try to take advantage of the challenge? By reckless driving? You're going to try to solve it while you're driving home? Yes, okay, sure. I will do that. I'll send a reminder. Okay. There we go. Okay, well, we got one problem left, and then we are done for the day. Then I'm going to have to show you guys a video. It is not math related, so I don't know if you would call it fun. I guess you'll decide when we get there. Number 5, a carousel at an amusement park rotates 3,024 degrees per ride. So A, how far would a rider seated 13 feet from the center of the carousel travel during the ride? So how is this one suddenly different? Okay. Well, it's in degrees, but What kind of problem is this? Is this like the previous one? No, see, this isn't circular motion. It's not linear or angular velocity. I'm wanting to know the exact distance that this guy's going to travel as he goes around in this circle. So what is that referring to? This is an arc length problem. Okay. What was the formula for that again? S equals R theta. Okay. So do we happen to know the radius? Yes, 13. That would be the distance the person is from the center. Okay, so 13 times. Now, I'm going to go ahead and multiply it by 3024, but what am I forgetting? It has to be in radians. So as I go ahead and plug into the formula, couldn't I just go ahead and convert it? I mean, we won't see the number of radians, but ultimately I think that's okay. I'm going to go ahead and multiply this by pi over 180 degrees, because this product will be in radians, and then we just simply need to multiply that by 13. Agree? These degrees are going to cancel here. So let's see what we're going to get. Document B. So 13 times the 3024 times control divide. We've got pi over 180 because we need it in radians. So how far is this guy going to travel? Okay, about 686 feet. Okay, for an entire ride, if he's 13 feet away from the center. Okay, so that takes care of part A. That's pretty easy. But now, what's it asking in part B? How much further would what? A second rider seated 18 feet away. So I'm going to do the exact same thing. I'm just going to replace what? Yeah, just replace that 13 with 18. So I'm going to highlight it, push enter. That way I don't have to retype the entire thing. I'm going to change the one little part I need. So if a person is seated 18 feet from the center, how far will he or she travel? Press enter, okay. 950 feet. There we go. Jack is absolutely right. I will push enter. But now, how do I find the answer to the question? There you go, because how much further did the person seated 18 feet from the center travel than the other person? And again, I don't have to retype these. I'm just going to highlight them. Subtract, enter again. So I'd say the person seated 18 feet out went about 264 extra feet on the same ride. Okay. And that makes sense. I mean, the further you are from the center, the further you're going to travel. What about speed? Are you going to be traveling faster closer to or further away from the center? Further. The further from the center, the faster you're going to be traveling. Okay. All right, there we go. Again, that's circular motion. Is anybody having any problems? Anybody not seeing where we got anything? Okay. Then let's go ahead, put our calculators back up here, and I will go ahead and get that video ready.